This is the beginning of our talk about data structures and data management. Having understood what we do in terms of collecting data out in the field, different procedures and the different types of data, we need to now look at how do we store this data in a GIS environment. In this lecture, we'll talk about, this is my table of contents, spatial data structures, in particular, the complexity of reality. How do we choose data set suitable for our intended application? And then we're going to look at one of the two types of data structures, one being vector structure. How do we store it? I will give you a basic introduction of the different types of how we used to store it in terms of the spaghetti data structure, and where we are in terms of storing the vector data in a topological data structure. We will also look at how do we create vector data, how can we use those vector data in spatial analysis. Now, the other type of structure we will talk about in the next lecture is going to be raster structure, and we'll talk more about that next lecture. Let's move ahead, talk more about complexity of reality. Spatial data structures. This is a representation of the relative location of features or phenomena occurring in reality relative to one another. When we collect data, we are collecting the data with respect to the features that exist in the real world. So a road is going to be next to a particular parcel, and the parcel is going to be next to a road. Now, when we collected this information, we actually collected, if we take an aerial photograph, it's inherent in the photograph, in the image. We also take the relative location of features into consideration when we start talking about spatial data. The power of your GIS comes from the ability to show the relative location. Show me all of the houses that are 100 feet off a particular road. That's a relative location of the houses with respect to the road, and vice versa. What data sets is needed is a major consideration in GIS application. Again, you can, if I'm doing a particular application and I want to look at, let's say, for example, property boundaries. Okay, I want to map all of the property boundaries in a certain area. I would collect, of course, property where the boundaries are located. So I'll also collect where the houses are located. But what I would not collect is temperature information, wind direction, pollution, things like that, because it is those sort of information is not the intent of my application to display that information. So you don't choose those information. You choose suitable applications for your intended GIS application. Here you see an example of spatial data in the different layers. Now, in GIS, you typically would collect data based upon the three cartographic primitives: point, line, and polygons. Using these three primitives, I can collect where my cell towers are located, so it's a set of point information. I can also collect land and water transactions, all right, a set of point location of where these entities occur. Any land use, here we have particular vegetation, we have trees, we have some corn, and we have carrots in this area being planted. Where are the farm holdings? Where are the farm houses? These are, in this case here, it can be points based upon the scale, or it can be polygons. I also want to collect ownership data. This is a set of polygons. This is one ownership, this is another in blue, another ownership, and in light green, another ownership. I want to collect also soil properties. One particular type of soil in dark gray, a light green, another particular type of soil, and in light pink we have another type soil property. I also want to locate where the rivers are. So this is a set of polygons, because I would capture both sides of the river, and that's another spatial data. The real world is very complex. As you can see here, a snapshot of the real world, but for my application I am only interested in getting parcels, districts, streets, soils, utilities, land use, topography, and hydrology. The buildings, the urban area, I'm not interested in, so I did not collect it. The subsoils area, I did not collect it. The water body, I did not collect it because it was not part of my intended application. So depending upon how well you choose the data set suitable for your intended application will ultimately affect your final results. So it's very important that you understand selecting the data sets suitable for your intended application is critical. Represented objects from the real world in a GIS. The central element of a GIS is the spatial database consisting of the integrated collection of your data. So your spatial database, as I said in previous lectures, you want to be able to represent that particular phenomena that you are trying to model accurately. So you choose data sets that are going to help you to present an accurate model depicting that phenomena. Spatial database is a realization of a model used to describe reality. So your spatial database, as I said before, always make sure that you back up your spatial database. Alright, you spend a lot of time to create models, to build your application. Make sure you always back it up. Now, there are two structures commonly recognized, one being your vector structure, and two is your raster structure. We're going to go into more detail into the vector structure in this lecture. This is an example of your vector and raster data. Here you have a snapshot of what the real world looks like, and out of the real world I want to be able to use a particular land use type, for example. So I would digitize a set of coordinates of the boundaries of the grassland area. So I have a polygon of the grassland area. I will also have a set of coordinates that are stored in our database for the marsh area, and also coordinates of a polygon that represents the lake and also forested areas. So it's a set of coordinates that is stored in the vector model. Now the same data in terms of the land use, I can store it as a raster. Each one of these rasters are data set in which data is stored as pixels, quite similar to your photograph. So my marshland area is going to be a set of pixels that are stored. My grassland is a set of pixels. My forested area is a set of pixels in green. And my lake and water body or river is also stored as blue, as a set of pixels. Same sort of explanation in this area here. In these three diagrams, we have vector data, and these three on your right is raster data, pixels, coordinates. In your vector data, a set of coordinates is stored for points. In your line data that are vector is a set of points that are stored to represent the lines. And in your polygons in vector, a set of points that are stored in the database to represent each polygon. In my raster, my lines are represented by a set of connected pixels, so the same value. My points are points of pixels that are the same value. Everything else that are shown in white, a value of 0 are stored. Alright, so when you have no data that I want to display in a particular layer, the 0 are stored for each one of them. And that means it's going to require a lot of storage space for raster data when compared to vector data. My polygons in my raster data, you have a set of pixels for each polygon defined, not only in the outer rim of the polygon, but also internally. Now, in our spatial database, we need to have a common coordinate system. We need to have, first of all, not necessarily a common coordinate system, but we need to have a coordinate system defining where these features are. And it can be any one of the projection system that we talked about in previous lecture. It can be UTM, it can be state plane coordinate system where eastings and northings are used. You also need to have the attribute tables of the features that you would have collected or captured in your data capturing procedures. Now, so you can look at this being the spatial component and this here being your attribute component in your GIS layers. There needs to be a linkage between your attribute and your spatial, and that spatial relationship is defined by the linkage between the two of them. Spatial relationship of the object with the surrounding objects, topological relationship describing where features are with respect to the other features. This is where the intelligence of your GIS comes into play. Previously, I mentioned how we capture the type of data we capture from the real world. We are limited when we start drawing features on a map. We are limited to 3 basic cartographic primitives. And this is applied to vector and raster data structures. We are limited to points, lines for streets, for example, or polygons for, this is a polygon here, for parcel boundaries, for example. Now, this here, points can vary in terms of the scale. If I'm looking at mapping, let's say, the cities of the entire world at a very small scale, each city is going to be represented by a point. Now, at a large scale, that city is going to be represented as a polygon. So all point lines and polygons are influenced by the scale at which the data is being displayed or captured. This is an example of the different data layers. This is using vector data. They're all using the same coordinate system because that's the only reason why they can be overlaid. I have in one layer soils, I have in the other layer land use, the other layer geology and floodplain, etc. I can overlay all of them and all of the information for each one of these layers, and the final result is going to have characteristics of all of these different data layers. The final result is going to be a polygon map, because I've overlaid a set of polygon data layers, and the attribute table is going to have description from each one of the attribute tables in each one of the data sets or data layers. Alright, let's go into a bit more detail into vector structure representation. Some characteristics about that. The fundamental primitive in your vector structure is our point. To represent point, line, and polygons in a vector structure, we use a set of points. These points are recorded by way of its coordinates in the real world. Features that are not of any interest in our application, we said we're not going to choose a particular type of feature in our application, then we're not going to store that in our database. Objects are created by connecting points with straight lines or arcs of circles. If I want to draw roads, I would start with a start or begin road point, and then any change in the direction of the road, I would digitize those features, and then I'm going to stop at a particular end of that road. It uses areas, lines, and points to represent objects. It does not fill space, meaning that features that are not of particular importance for that application, I would not capture it. So there is no value being stored in the database for it. Another characteristic, and I put this in capital letters, tells where everything occurs. Wherever, whatever feature I want to capture, it tells where that particular feature is with respect to other features of the same characteristics. And it uses a basic line algebra, where a point is defined by an x and a y coordinate. A line is going to be defined by coordinates that define the extent of that line. So what is stored for that point, for example, is 1 coordinate. What is stored for the line is 4 coordinates. And what is stored for the polygon is 6 coordinates. Polygons start and end at the same point, and polygons need to be closed. How do we create vector data? The number one method of creating vector data is by way of digitizing, and we spoke about that earlier on. It's the main method of data input. Traditionally it utilizes hard copy maps on as a basis for digitizing. And there are a number of methods which we spoke about earlier on. One method is manual digitizing. It uses existing maps. Using a digitizing board, you have to define a coordinate system for it. You have to georeference that map, meaning that it has to have a on the map control points where we can transform from our digitizer coordinate system to our ground coordinate system. And you can digitize using a number of methods. It can be wherever there's a particular feature I want to capture, I would use the digitizer puck and capture that point, press the button, and it capture the XY location of it. Or it can be on a stream mode of this digitizer, meaning that every 10 seconds the system will automatically capture a point. So you have to make sure that you are moving along the particular feature, and the system will automatically capture it in the database. Scan digitizing, we spoke about in earlier lectures, makes use of a scanner, produces raster data initially, and then we can convert that raster or pixel data through a vectorization process, and there are quite a few software out there that can convert from raster to vector. And there are certain inaccuracies involved in the capturing of vector data from a scanned image, and we will talk about that later on. The third method of digitizing is the on-screen digitizing, where I would use a georeference or ortho image, raster image as a backdrop, and then create layers, empty layers, and then start tracing out on those layers on the computer monitor using the GIS software to create my layers. It requires a computer environment. This is a diagram of when we compare scan digitizing with manual digitizing. Now, which one is better? Which one is the preferred method? The answer to that is neither. It all depends upon the intended GIS application. If I have a large number of maps to digitize, let's say a few hundreds, obviously I'm not going to digitize each one using a digitizing table. I'm going to use a scanner to scan it in. But note fully well I'm going to have to do a lot of post-processing. And each one of these requires some more information in terms of how do I extract my point line and polygons from my scan image? How do I vectorize it? How do I add attribute information? So it requires a lot of more post-processing steps. Even though it's much faster, post-processing is much more demanding. My manual digitizing, I would it's easier in terms of if it's a few maps that I need to digitize. I'll just set up the digitizer, digitize the features, add my attribute, do some editing and georeferencing, and I'm done. And I can create my point line and polygons. Now, all of these, the scan digitizing and the manual digitizing requires some building of intelligence in the database, being able to link where the point line and features are with respect to other features. Okay? And again, in this comparison, I want you to know that the preferred method is neither. It all depends upon the intended application. Another method of creating vector data is by way of field survey methods. Field survey methods produce coordinated values that are used directly in plotting features. So when this licensed land surveyor go out in the field with his total station and start capturing or collecting data using his data collector, he's actually digitizing out in the field with getting the X, Y, and Z values of features, and then come back in the office and download it. Though the data sets that are downloaded is a set of point data sets. Alright, it's a point location where features are. Field survey methods includes GPS. You're using total stations. Data sets are stored in digital format in the data loggers or using pocket PCs, and it's easily downloaded into your GIS system. And as I said before, it creates vector data. Now, how do we store vector data? Traditionally, the vector data was stored as a spaghetti structure. Long ago, they used to use that particular structure to store your vector data. Spaghetti, and the other method is topological structure. Let's look a bit into each one of them. Your spaghetti data structure is a collection of coordinated strings with no inherent structure, hence the name spaghetti. Wherever a particular feature occurred in the database, the X, Y, and Z values are stored for that particular point, or that particular line, or polygon. The data structure is really a map expressed in Cartesian coordinates. Although the spatial features are recorded, the spatial relationship between these features are not encoded, meaning that the intelligence was not explicit. It was not programmed into the database, into the spaghetti data structure. It was very inefficient for spatial analysis since it must be computed. Those spatial relationships needed to be computed. And it also, which is a drawback to it, it stored data redundantly. Now, in any database, you try to minimize the amount of redundancy in the database. I have the following figure shows an example of your spaghetti structure. So let's look at it. This is the example of your spaghetti data structure. If I have a feature, this is my map, okay, the original map, and in order to store this map, I have a set of polygons. Alright, polygon 63, polygon 64. I have a line, I have a point number 10, and my line is point number 23. How is that stored in the spaghetti data structure? What was done is that in the tabular form, the database contained the feature type, whether it's a point, line, or polygon. It will put in also the number, or the unique ID number for each one of those features. So my point had a number, a unique number of 10, which is this number here. And its coordinates are stored. So it had an X and Y location for that single point. For the line number 23, and that's the ID number, and the series of X and Y coordinates are stored as a string. My polygon, you have polygon 63 and 64, 63 and 64, and for 63, the series of X and Y coordinates are stored. It's a closed loop, and for 64, the series of X and Y coordinates are stored. What is being repeated here between the two polygons is that you see this boundary here between polygon 63 and 64, that is stored for polygon 63. And it's also stored for polygon 64. So that is the redundancy that I talk about. And that's not a good thing in this representation. To improve upon that, they came up with a topological structure. It's the most widely used method of encoding spatial relationship. It's also called map-based topology by certain software developers. What is topology? And if you can learn this definition, topology is the mathematical method used to define the spatial relationship between your three cartographic parameters, which are point, line, and polygons. So topology, in a simple explanation, is the ability to represent, using mathematics, the relationship between points and lines and polygons. In your map-based topology, it made use of an arc node data structure, which is a typical form for topological structures. So tables containing all of this information, where arcs are located, nodes are located, and polygons are located. And it gives us an explanation for each one of them. An arc is a series of points that start and end at a node. So you have it's ultimately, in some books, they refer to the line as an arc. A node is where two or more arcs intersect. That defines a node. A polygon consists of a closed chain of arcs that represent the boundaries of the area of interest. Topology is recorded in three data tables using the map-based topology, one for each spatial element. So there's a map for arcs, there's a map for nodes, there's a map, there is a table for each one of them. So a table for arc, a table for node, and a table for polygon, and a fourth table that contains the coordinates for these points. And there's a very good figure that I want to review with you in the next slide. This is using the arc node topological structure. We have a map of an area, and as I said before, there are four tables. There's a polygon table, there's a node topology table, there's an arc topology table, and then lastly, this is the coordinate tables. Now, let's look a bit more detail into the map being displayed here. The capital letters are the ID numbers for the polygon. So this entire area here is my polygon A. The outside area, outside of my map, is ID number E. This area here is my polygon area C. And inside this loop area, this island polygon is polygon C, and my point, the system assigns a polygon ID for that point, and it is polygon D. N, the capital N, so N1 to N4, capital N, it represents nodes. So I started when I started digitizing, I started from N1, a vertex is added, and then I ended with a node 4. Then I start digitizing here, node 2 with a vertex, and ended with a node 3. The line that joins between two nodes is defined by an arc, which is lowercase and a number. So in terms of this diagram, the arc between N1 and N3 is A3, which is arc 3. And that's the explanation for the entire map being displayed here. The system creates this in the background once it's using an arc node topology structure. My polygon C has one arc, so it's arc 7. My point has an arc, but there's a null value there, so the system does that automatically. So how does the system use this information to create these tables? These tables are not done by the end users. The GIS software would create these when it builds topology. As I said, your polygon topology, the polygon table is going to have each one of the polygon IDs, A to E, and where the arcs are used to define each polygon. So my polygon A is defined by arc 1, arc 3, arc 5, and arc 4, and that's what here it's showing. Arc 4 is missing actually. My polygon B define all of the arcs. Also, you have to put in the arc 6 and arc 7 is also, because this is an island polygon, you put that in here. Here. Now my nodes. Node 1, the system would label node 1 to node 6. Node 1, node 4, node 3, node 2, node 6, node 5. And then for each one of the nodes, list out the arcs that they are defined. For example, node 1 is defined by arc 1, arc 3, and arc 4. Arc 1, arc 3, and arc 4. Node 2 is arc 1, arc 2, and arc 5, etc. My third table, my arc topology table, it all depends upon the direction in which my arc was digitized. In this case, my arc 1 was digitized from node 1 to node 2, so node 1 to node 2. So and I will put in node 1, node 2. My left polygon, if I'm going in this direction, the left hand side is going to be my polygon ID E, and my right polygon is going to be polygon A. Each one of these arcs, the system would automatically generate the start node, the end node, the left polygon, the right polygon. And the fourth table is this one here, the arc coordinate data. For each one of the arcs, the system would have the coordinates for them. So this table is linked to this by way of this column. This is linked to that. And from this, we will have the nodes linked to it. We'll also have the arcs being linked to this, and that's how it gets the and this table here will get the arcs linked to this table here. That's how you get the ground coordinates for each one of these features: the polygon, node, and arc topology. And in summary, the system creates this topology in the background, and this is where the intelligence of a GIS database comes into play. This is some notes about the four tables. Polygon topology table are created. It shows the arcs that make up the boundaries of each polygon. Also created is the node topology table. For each node is defined by the arcs to which it belongs. And the arc topology table defines the relationship of the nodes and the polygons to the arcs. So this is where you're going to have the start node and the from node. and which one is the left polygon and which one is the right polygon. And linking all of these together is going to be my arc, my coordinate data table. Very useful concept. Another type of topology that is more popular in the GIS market now is rule-based topology. It is a topology that is implemented using a set of rules, and using object-oriented programming you can specify a number of rules in order to build a different type of topology that you want to build. It is defined as a set of rules defining the spatial relationship between features and the constraints placed on those spatial relationships. And one of the popular GIS software has this rule-based topology, and examples of them, and it's easier to implement and easier to understand than our map-based topology. But examples of them is for point features, it must be covered by a boundary of a polygon. It must be within a polygon. It must be covered by the end point of a line, things like that. So it's a set of rules that you would execute and run the topology tool in your GIS software in order to build that intelligence using the number of rules that is defined within the software. This is an example of the rule-based topology. As you can see here, lines must not have dangle nodes, meaning that it must not have any overshoot. So if the system checks the database and there is any overshoot, it will delete it, making sure that the lines are actually closed and there are no overhangs. Your polygons, for example, must not have any gaps. So what the system will do is search the entire database. If there's a gap, it will define that gap as a polygon. Another rule that they implement is your polygon must not overlap. So if I have an area where polygons overlap each other, which is not a real world scenario, obviously when they were digitizing, there was an overshoot of that polygon into the other polygon. So what the system will do is remove that overlap and offset it by a certain distance. Alright, so a number of rules, and it makes the system much easier in terms of implementing these rules and more flexible. And there are a multitude of these rules. Now, this concludes our first part in our discussion regarding data structures and data management. I advise you to download the PowerPoint notes page, review the material, make sure you understand it, and we'll continue with the next lecture.